Quindi dopo ti scuto. Oh, niente, ce la teniamo così, perché cioè qui non credo, quando parte si accende la luce scatta, ma va l'aria, no?
Bene, lascia stare.
No, sei stata.
E se parte con
Adesso sta te, prima io adesso no, che non sta bene. No, no. No, ma io non tocco niente.
Gira per controllare che quelli da casa poi ci sentono.
Sì, ci sento, ci sento.
All right. Ecco, guarda, anche Stefano siamo a posto. Thank you for coming. It's a pleasure to introduce the today speaker, Ciro Pinto from IASF Palermo. Ciro graduated in Napoli with Maurizio Paulillo, which many of you know very well, and then moved to Sron for the PhD, and where he did some work with ULXs. And then a long postdoc of 5-6 years in Cambridge, UK with Andy Fabian. His scientific interests are mainly related to the ultra-fast outflows, cluster of galaxies, and high-energy astrophysics issues at large. He's also a member of the New Athena Science Study Team, the top-level board of the new mission. And today we'll talk us about why it's so fun to the Eddington limit and compact objects. For those interested now or after, there are cookies and confetti that I don't know how to translate, but you got it. Thanks.
Thank you, Andrea. That's probably the best introduction I ever received. Good morning, everyone. Buongiorno a tutti. Thanks a lot for inviting me here, and also good morning to everyone from home who's attending right now. Yes, I'm an authentic Napoletan, but I've traveled the world, so I had the fun and the luck to work with many people and get many interests. Today, I'll try to explain to you why it's so fun to go beyond the Eddington limit at different mass scales. And anyway, before starting, I want to thank particularly my PhD, current and former PhD students who helped me a lot. And many of the slides and plots you'll see today are actually from their work, not really mine. Anyway, let's start. There is a little bit of lag. Okay. So the goal of today is try to give you kind of my perspective on how black holes grow and interact with their surrounding. Many of you will know that stellar mass black hole grow by ripping off matter from nearby stars. Same also for supermassive black hole, gathering matter from either destroyed stars in tidal disruption events or from the interstellar medium in the center of the galaxies. Not all the matters enter onto the black hole. Much of it is also expelled in the form of jets, winds, or any kind of outflows. And you can see this kind of feedback to the interstellar medium in the form of either interstellar cavities in the interstellar medium around supermassive black holes, or even interstellar cavities on stellar scales around binaries, stellar X-ray binaries. I'll show you some examples today. So it's a big cycle, and it's very important also to figure out how do we get from stellar mass to supermassive ones. For this reason, I'll try to face off different point of view from both the stellar mass regime and the supermassive regime. And I hope that there will be time at the end of the talk to provide you some future prospects. So I suppose that there might be some students or people who don't work right on accretion or compact objects. So in this case, we know of black holes and in general compact objects. When a star explodes, the nucleus, a massive star explodes, the nucleus collapses due to gravity. And whether the mass is above or lower than about 3 solar masses, you end up with a neutron star or a black hole. We know of black hole when they start to rip matter from nearby stars. Now, they need to be kind of activated because they don't radiate. But if they rip matter from nearby stars, from the Roche lobe, then the matter accretes in the form of an accretion disk, because these objects, they rotate around each other. So matter doesn't go straight into the black hole, but it forms a spiraling accretion disk around the compact object. The temperatures in the center can be pretty high due to interaction between the particles, and virtually this disk radiates in all wavelengths from radio to gamma rays, thanks also to other kind of processes. It's not just the black body emission. There is a lot of comptonization emission from the inner region, where there is a hot cloud of electrons with temperature up to 10 to the 8 Kelvin. And so you can find a lot of different type of emission processes in the form of black body from the disk, comptonization from the inner corona. Stellar mass, supermassive black holes, same. Also here you have emission from the disk, although the disk here is much larger. Supermassive black holes, accretion disk can even be something like the solar system. So temperatures are much lower and the emission peak is in ultraviolet. But you also have comptonization from the corona that is around the compact object, in this case, the supermassive black hole. And some of the matter goes back from the corona onto the disk, which is cooler, and then radiates through fluorescent lines and similar kind of emission, including a Compton hump around 20, 30 kV. You had a talk from Andy Fabian a couple of weeks ago, so I guess now you know everything about reflection, or kind of. So I won't talk about reflection today. Anyway, black holes, somehow they know about the host galaxies and vice versa. The galaxies seem to know about the type of black hole that is in the center. In fact, if you compare the mass of the supermassive black hole and the mass of the bulge of the kind of spheroidal inner part of the galaxy, they are very well correlated with each other, surprisingly over different orders of magnitude, which in other words is telling us that these two objects are growing together. And it's really weird, because the supermassive black hole is a scale smaller than the solar system, while the nucleus of the galaxy is kind of kiloparsec. So it's very difficult to explain these two things. But an interesting thing is that if you compare the radiating energy of the black hole via accretion, I guess many of you recognize the Einstein formula here, modulo an efficiency, which is typically 10, 20% for an archetypal typical black hole. If you compare this energy to the binding energy of the nucleus of the galaxy, you end up having a ratio of 30. So potentially, if the black hole managed to release a substantial fraction of its energy onto the nucleus, he has the effect of disrupting nucleus, or at least influencing the star formation rate in the nucleus. And this might be the reason behind this correlation. In other words, if there's too much material and then the black hole decides to go on a diet through outflows, it will put on a diet the nucleus of the galaxy as well, something like this. And in fact, an interesting thing has been found recently. The star formation rate has decreased, and the moment in which it decreased, it was basically when the AGN of active galactic nuclei reached the peak of the emission or the accretion. In other words, as soon as the black holes start to accrete sufficiently and therefore radiate, apparently star formation has decreased. So maybe the black hole is kind of a turning off engine for star formation in the inner part of the galaxy. Weird thing is in the very early part of the universe at high redshift, they start to find a lot of massive black holes that are way more massive than the expectation of given the stellar mass of the galaxy. So it looks like you first grow these supermassive black holes, and then they have an effect on the growing of the galaxy itself. But perhaps the weirdest thing to understand is how you manage to obtain them, because massive black holes of the order of 10 to the 8 or 9 solar masses are found at redshift larger than 6, when the universe was less than 1 giga-year old. And that's a short amount of time in order to grow such a huge object with the vanilla Eddington limited accretion. Okay, if you assume that you cannot accrete more than Eddington, then you have to start with a stellar mass above 1,000 solar masses. Okay, if you assume. But since we know that there are some objects that accrete beyond Eddington, then if you assume super-Eddington in the early part of the universe, then you may start the process with a more realistic mass of the order of 100 or so solar masses that is the typical result of the supernova explosions, especially at low mass, at low metallicities. So for some of you who are not familiar, the Eddington limit is a limit on the luminosity, and is the luminosity at which under spherical geometry, the gravitational force and the push of the radiations are equal. So in principle, under this regime, you cannot have luminosity higher than this. And this luminosity is obtained by equating this formula, and you can see it's basically a function of the mass. So a solar mass star has an Eddington limit of 10 to the 38, a typical 10 solar mass black hole, it would be 10 to the 39, and so on. In which case, for a vanilla 10 solar mass black hole at 10% accretion efficiency, it's something of the order of 10 to the -7 solar masses per year. But this assumes spherical geometry, and we know that accretion disks are not spherical, of course. So, what kind of objects we need to look at if you're interested in super-Eddington accretion? This is a very incredibly simplified scheme of accretion. Stellar mass regime, below 10 to the -3, the Eddington limit, we have quiescent X-ray binaries or low luminosity AGN. The higher the accretion rate, then you will go through Seyfert, galaxies, quasar, and above Eddington, you obtain such a kind of accretion in some of the local narrow line Seyfert one and tidal disruption events. So they are excellent targets for this regime. In the binary regime, there are the ultraluminous X-ray sources. Now, the reason for which I will focus slightly major part of the talk on ULXs is because they radiate in the X-rays. AGN radiate in the ultraviolet, and here there is a lot of extinction from the interstellar medium. So there is a large uncertainty on the intrinsic luminosity and therefore the Eddington limit, while in ULXs we don't have this problem because most of the emission is in the far UV soft X-rays. So that's why we'll start first with stellar mass compact object. And the very interesting thing is how, as I mentioned you, how do we get from here to here, from a small to a supermassive black hole? There is a huge gap of something like 2-3 orders of magnitude in mass. If you assume low metallicity, which means the first generation of stars, since the winds of the stars would expel little radiation due to the low opacity and due to the low quantity of metals in the shell of the stars, the leftover nucleus will be larger, and therefore you may end up with a larger black hole at the end of the star life. But we're still talking of something like 100 solar masses. So there is a massive gap of something like 2-3 orders of magnitude. Gravitational waves help, but so far we have only found typical black holes merging and forming something like 100-150 solar mass black holes. So we're still far away from the intermediate mass black holes, which is why, of course, ultraluminous X-ray sources are very interesting. This is still kind of an early field because it kind of boosts since 2000, right when XMM Newton and Chandra were launched. And there is a reason for that, because these were new technology and powerful missions that enabled to significantly improve this field of research, and I'll show you why. So for some of you who are not familiar, there is an empirical definition of ultraluminous X-ray source. It's basically an object that is brighter of a typical 10 solar mass black hole radiating at the Eddington limit. So the Eddington limit of a 10 solar mass black hole is approximately 10 to the 39 per second. So these objects are brighter than this, which means either they are super-Eddington or they are intermediate mass black holes, or in principle, it can be both. It can be slightly massive black hole, but with a high accretion rate as well. So it depends on the circumstance. And they are, by the way, off nuclear, so not to be confused with the supermassive black hole in the center of the galaxy. They tend to be found predominantly in high star-forming, low metallicity galaxies, where you would expect a lot of black holes and low metallicity, therefore high mass X-ray binaries. Okay, And so in the beginning, everyone thought, okay, these are either black holes or intermediate mass black holes. But that was the beginning. In fact, actually, there were some objects which would look like Eddington limited intermediate mass black holes. For instance, there is this object, the hyperluminous X-ray source, because it's brighter than 10 to the 41 Hz per second, ISO 243 minus 39 in this object here, which turned out to be the nucleus of captured galaxy in this other galaxy here. And this object goes between bursts and quiescence phases, which is typical of X-ray binaries, okay? Except that the luminosity is really high, and recently there was a delay in the outburst, and then there was no outburst anymore for the last 10 years or so. So actually people start to think maybe it's not a bona fide X-ray binary, it's more of a sort of failed tidal disruption event, which would suggest a kind of low mass end of supermassive black holes rather than a bona fide intermediate mass black hole. And the luminosity peak would suggest a mass above 10 to the 5 solar masses. We know there are supermassive black holes with this kind of mass in small galaxies. So not really sure about the interpretation of this object. Anyway, the curious thing is that most ULXs behave completely different with what you would expect from a Eddington limited object. And you can see it here in the plot on the right. The yellow spectra that you see here are models for soft state and hard state of standard galactic X-ray binaries. And you can see that spectra of ULXs, on top of being, of course, 2 orders of magnitude brighter, they are way softer than this one, much, much softer, with a massive cutoff around 10-ish kilo electron volt. Okay, normally you would look at a spectrum like this, and then you would say, perhaps high accretion rate, very cool saturated corona, rather than low accretion rate, Compton thin corona and stuff like that. But spectra are kind of different with each other. They tend to be very different from hard all the way to soft. But the most important thing is whether you consider either the soft or the hard, which is soft ultraluminous and hard ultraluminous, all of them, they are still much softer than the galactic X-ray binaries. For this reason, we are not talking of different states in the ULX regime. We are talking of different regime in one state, the ultraluminous state. Okay, so this is all characteristic of one specific state, the one above a certain luminosity. Spectral component, a little bit more complicated than galactic Eddington limited binaries. You end up needing normally a third component. So there is a cool component for perhaps the outer disk with a temperature around 0.2 keV, typical hotter disk temperature around 1 keV or above. But as soon as you have sufficient statistics around 10 keV, for example, if you include the NuStar on top of XMM or Chandra, you end up requiring a third cutoff-like component, which could be either some weird thing happening in the inner outer part of the corona, or there's something like the surface of a neutron. It could be something like emission close to a neutron star, okay? If the compact object, of course, is a neutron star rather than a black hole. And now we start talking about neutron stars, by the way. Of course, if it's Eddington limited object, you would expect the luminosity to increase with the temperature to the 4th power. And the curious thing is that none of these objects behave like this. This object, NGC 1313X1, through a campaign that we did back in 2020, you can see that luminosity kind of increases with the temperature to the 4th power, and then above a certain threshold, it deviates. Temperature goes down, and then the luminosity increases. It's like the accretion rate is increasing, but beyond a certain threshold, something cools down the accretion disk or prevents you from seeing the hotter inner part of the accretion disk. Maybe wind, obscuring the inner region. This was studied even further, for example, by some of our students. Francesco Barra, he discovered deviations above a certain luminosity in both the soft component and the hard component. The plots that you see here basically how the luminosity of the 0.2 and 2 kb component increase with the temperature. They kind of deviates above a certain threshold. And if you assume that this threshold is the Eddington limit and beyond something is happening, then you get a constraint onto the mass of the compact object, because the Eddington limit scales with the mass of the compact object. So if you assume that this luminosity above 10 to the 39 is the Eddington limit, then the mass, of course, would be something like 10 solar masses. Okay. For these objects, 1313X2, this doesn't really work because the cool component, it's kind of anti-correlated here. So the luminosity goes down with the temperature. So if we would assume kind of Eddington behavior and then a deviation, then it would suggest that the deviation would start below. So we would end up in getting a lower mass compact object, or a very tiny black hole, or even a neutron star. And remember the name of this object, by the way, because in a minute we'll come back. Speaking of neutron stars, this research field was shocked back in 2014 when Matteo Bacchetti and colleagues, they discovered in M82X2 pulsations. So it was a classic ultraluminous X-ray sources that people believe it was either a black hole or intermediate mass black hole. They found pulsations. Pulsations means neutron stars, because you can't get such a high luminosity with a white dwarf of 10 to the 40 ergs per second, not even in an amazing hydrogen burning regime. And the curious thing is that in the 25% of the high quality data where you will be able to detect pulsations, they find pulsations. So also another object like NGC 5907, and by the way, also this object. So this object is also another neutron star. Okay. So at least 25% of the ULX in the nearby 15 megaparsec are neutron stars. And given that in our galaxy, pulsations are not found in all the neutron stars, then we know that this is a lower limit. Most likely it's going to be above 50%. Okay. Magnetic fields, there is a little bit of debate on whether they are classic 10 to the 10 or 10 to the 12 magnetic fields or magnetar-like, but they can't be magnetars, because if they are magnetar, then, as I'll show you in a minute, the magnetic field would truncate the disk, and you will have propeller effect, and there would be no way to bring the matter close enough to radiate significantly, unless everything is extremely beamed. But these objects are not beamed. Cyclotron lines would help, although there are very few putative detections, and sometimes they also disappear. So it's very difficult, and it's a shame, because the cyclotron line will tell you right what would be the amount of magnetic field. So we still I'm not really sure on the magnetic fields of these objects. But we certainly know that some of them are neutron stars. Oh, and here is normally how you will measure magnetic fields. The problem is that it depends on whether you assume electron or a proton cyclotron line. There are 3 orders of magnitude in the measurement. Although this line appeared to be narrow would suggest a proton, because protons are more massive, and then it would be 10 to the 15 Gauss, but I'm not really sure about it. Anyway, so this is the current sample of pulsating ULXs. There's plenty of them, and the thing that you can figure out from this plot is this column here. The change in the period is pretty high. I mean, 10 to the minus 10 per second is a lot if you integrate it over the course of a year or years, and this normally would suggest substantial amount of accretion rates. Typically pulses are of the order of seconds, so you detect pulsation by scanning the power density spectrum around the Hertz regime. For some of them, only a few. There are ideas on the companion stars. And speaking of companion star, we're talking, of course, of X-ray binaries in other galaxies. At megaparsec distance, you can only observe massive companions. You cannot find a solar mass star at 4 or 5 megaparsec distance. In fact, some of these ULXs have as a companion star red or blue giant star, as suggested by some absorption bands into their spectra. And what you see here is a possible scenario in which a ULX is formed. So you would start with a massive main sequence star separated by 1,000 sun radii from a smaller main sequence stars, and after a few dozens of mega years, there will be the phase of common envelope around the main sequence. The massive stars was becoming AGB, and then after the explosion of the star, or even a planetary phase, then you would be left with a white dwarf, which by accretion would become a neutron star, and therefore you would be left with a neutron star ULX. This is one of the several possible regimes. There are also situations in which you would end up in finding a black hole, and it really depends a lot on the metallicity of the galaxy. If the metallicity is like our galaxy, most of the binaries would end up having neutron stars. If the metallicity is very low and you are in the first phases of the outburst of the galaxy, you would end up with a lot of black holes as a compact object. So it really depends on the phase of the outburst and the local metallicity. The interesting thing is that according to accurate calculation of the Podzialowski group, you can see that the accretion rate can exceed the Eddington limit by a couple of orders of magnitude. And it's very important to notice here the timeline we are speaking of. Here we are speaking of something like a mega year or 500,000 years, no, more than 10 to the 5 years. Remember this 10 to the 5 years because it's very important to understand what will happen to the surrounding interstellar medium. So for 10 to the 4, 10 to the 5 years, you can definitely achieve super-Eddington accretion. And how it will look like. So let's assume a blob of matter super-Eddington at super-Eddington rate accrete onto the compact object. The radiation will be so strong, then the disk will swollen, and at some point on top, the gravitation is exceeded by the radiation pool, and then it will launch powerful wind at escape velocity. In the around 50 Rg, the escape velocity is 0.1, 0.2 speed of light. So you would expect to find ultra-fast outflows, okay? The same one that Tom Basie and friends normally study in supermassive black holes, and one of the main topic of the subways project here. So people have been looking for this stuff in ULXs using perhaps the wrong detectors for many years. Yeah, this is just how it would look like, a kind of volcanic explosion. And the interesting thing is that the wind is so thick and broad that it will give the system the shape of a funnel, which means depending on whether you see face on or edge on the source, from top or at angles, the system will look completely different. Hardish, if you look face on, softer and softer if you look at higher angle, because the inner part is completely obscured by the wind. Okay, so the opposite of neutral absorption. Neutral absorption normally will give you harder and harder spectrum, but here you are removing primarily the harder component from the inner region, so the spectrum will become softer and softer. However, if you have a neutron star in the center, you have to take into account the magnetic fields. And even if you have 100 times the Eddington limit of a neutron star, for a magnetar-like magnetic field, which means from and above 10 to the 14 Gauss, you will basically kill the wind because the disk gets truncated at high radii and the matter will be channeled onto the polar, on the poles of the neutron stars, plus there will be also the propeller effect. So much of the matter will be thrown away, and you won't really manage to achieve luminosity of 10 to the 41 ergs per second, because some of these ULX and neutron stars, they shine at 10 to the 41 ergs per second. Crazy, 500 times the Eddington limit. So there is a good possibility that the winds, the magnetic fields are below 10 to the 13 Gauss. Here you may have a coexistence of the spherization radius, which is indeed where the radiation pool exceed the gravitational force, and you launch winds. And then inside you have the magnetosphere around the neutron star. And this is typical magnetic fields that you find in our galaxy, like for example, in Hercules X1, magnetic field dipole components of the order of 10 to the 12 Gauss. So there is a point in each life in which Hercules might have been in the past or in the future ULX. Therefore, you expect to find strong winds in case the magnetic fields are not above the magnetar threshold. So people did not find unambiguous evidence of winds in these objects because they were using the CCDs. The problem is that, as I will show you soon, due to the very soft spectrum, most of the lines are found in the soft band, not the hard band. Normally, people would use the iron K region to search for outflows, but these spectra are very soft. So most of the lines are iron L, and there the spectral resolution of CCD is really crap. So you would use rather gratings, and the best one in terms of effective area is the RGS, reflection grating on top of XMM Newton, thanks to the grating here, which scatter half of the light onto the grating array. You manage to achieve a resolution of 10 to 100 times better than the CCDs. So that's definitely the instrument that people should have used, stacking data on these objects. We tried to do this in 2015, and we find for the first time very strong emission lines consistent with the Lyman alpha complex of many ions, such as oxygen 8, neon 10 plus helium-like triplet emission, and neon-like, like the iron 17. So that would be slow-moving gas because the velocity are within 1,000 kilometers per second. But on top of this, there was absorption from the same ions, but blue shifted by 20% of the speed of light. So plasma moving towards the observer direction at 20% speed of light, which for an X-ray binary is crazy. There is no X-ray binary in our galaxy with such an unambiguous detection of 0.2 or even above speed of light winds, not jets, of course. We detected also another object, and this was the very first evidence of radiatively driven super-Eddington winds. This object, 1313X1, as the number would tell you, is a double luck object because we also find the counterpart of this outflow by stacking 300 kiloseconds of data of CCDs around 8.5 and 9 kilo electron volts. Same speed, just a hotter component. So this could be also multi-phased plasma because there is no way you can have iron L and the iron K absorption from one component. You need more. There is too much difference in temperature here. How do we search for this line? We take high resolution spectra and we scan them. The traditional method is you apply a moving Gaussian, you change the position of the galaxy, of the Gaussian, calculate the change in chi-square, take the ratio, and you have the single trial significance, okay? And then you perform Monte Carlo simulation to figure out the probability that the line is true or fake above a certain threshold, which could be 3, 4, or 5C, okay? This is very time consuming, and for this reason, recently, we are mainly using a cross-correlation method. So we create models of Gaussian lines, cross-correlate with the data, which is a calculation, not a fit. So orders of magnitude faster. And then we perform the same thing of simulated spectra. In this way, you gain in speed by 4 orders of magnitude. So if by any chance you still use spectral scan to search for lines, I would strongly recommend in the future, but especially with my calorimetric data, which is more heavy, certainly heavier, with many channels, to consider this. And I have some bonus slides if you want to know a bit more about this correlation method, okay? I also have a tool on my GitHub in case you want to download it and use it. Anyway, we use this cross-correlation method and we found emission lines in almost all ULXs in a sample of 19 objects. And we found also absorption lines, but the absorption lines were indeed shifted with respect to the rest frame laboratory wavelengths, and they were also less abundant. I mean, the fraction of ULXs showing absorption lines was something like 40–50%. But the number increased with the statistics of the data. The more data we have, the more lines we find, which is really great. The interesting thing as well is that the number of lines increase when the source is softer. This is the hardness ratio, which is basically the slope of the spectrum. Low number means soft spectrum, large number, harder spectrum. And you see most of the lines, more lines are found when the source is soft. And that makes sense because when you see face on, you see through the low density part of the wind, low number of lines, and you can see the innermost region that is hot, and you are basically here. And then at higher inclination, the winds start to absorb more and more the inner region. So the hardness ratio decrease, but the number of lines increase because you have absorption and you are also decreasing the continuum. So it's easier to find lines. And that was already telling you something about the shape of the objects. I should probably speed up. So how do we model this? Photoionization gas models. You take the SCD. You can see ULX SCD is much softer with respect to AGN1. And therefore, you expect a lot of absorption lines from low ionization ions, such as oxygen 7, oxygen 8. So soft band is the place where you would look for lines in this object, rather than the iron K band. And the modeling and also the search for these winds, you want to be also more efficient. Gaussian lines, you have the sigma only for individual lines. If you want to increase the significance and also have a better idea of physics of the object, you would create the grids of photoionization gas in absorption, scan the spectrum in the parameter space of ionization parameter, which is the best friend of the temperature, line of sight velocity, line broadening, and color density of the wind. And when you find a strong peak with delta cis at above 20 or 25, then you find something like a 3 sigma detection in these objects. To better visualize this, you would plot this in a 2D scale of 2D map of velocity and ionization parameter. And then you start to find also interesting pattern. When the source is harder, you have a dominant hotter component of the wind and also faster. And when the source becomes softer and brighter, you have an emerging very strong and even higher significance. Here we're talking of 4.5 sigma component at lower velocity and lower temperature. So what is telling us this? It's also found in AGN, and I will show you an example later on. It's telling us the shape of the wind and the disk. So we are having a higher luminosity, higher velocity, and a higher temperature. The color is the ionization parameter when the source is harder. And this is right to what you would expect from a funnel shape. Face on, you can see the inner part of the disk, so hard excess, and the wind will be coming from the inner region, so faster, but also hotter. Instead, when we see at a higher and higher inclination, we will start to be dominated by cooler and cooler and slower component of the wind coming from the inner region, which is obscuring also the inner part of the source that will look like soft, and we are right here. Of course, these are only a few objects. For this reason, we have requested for a very large program with XMM, who was just approved in the last program, and the observation has just started this month. So stay tuned because there will be news on the population of this diagram in the next months or years. Okay, so we look forward to this. These winds are very powerful. If you compute the kinetic energy in terms of the outflow rate, which depends on the velocity, and you end up in having this equation, which is basically velocity of the wind cubic divided by the ionization parameter times the solid angle of the wind and the clumpiness, how the wind is porous. If you assume some the solid angle depending on the detection of fast winds in ULXs, which is something like 30–40%, which gives you a solid angle estimate, and the clumpiness from some equations or some theoretical simulation, then you end up in having a kinetic luminosity above 10 to the 39 ergs per second, which means that basically 50% of the energy is lost to launch the wind. But it's very important because this value is comparable to the energy that you need mechanically to blow this interstellar cavity that are found around many ULXs. So the ULX wind is blowing this interstellar cavity, and if you compute the amount of time that you need something between 10 to the 4 and 10 to the 5 years. That's why in the beginning I told you, remember the 10 to the 5 years, that is this kind of instability mass regime where there is a high accretion onto compact object. It's very important because this explains that this object can be super-Eddington for 10 to the 4, 10 to the 5 years, and blow these massive cavities via winds. Okay, 50% means that 50% of this super-Eddington rate ends up onto the compact object, which would naturally accrete above Eddington. Okay, apparently. So perhaps the net accretion rate would still be super-Eddington by a factor of a few, of course, not a 10 or 1,000. So in the last part of the talk, I would like to show you how we use these same techniques and framework to figure out what happens in supermassive black holes. Okay, here there is a massive group on AGN, so I guess I can go fast on this because many of you work on this and you must have heard the talks from the subway team. So AGN, they also have winds just like X-ray binaries, slow winds, which are found both in X-ray and ultraviolet, and are called typically warm absorber. In ultraviolet, they tend to be called or optical narrow line, broad line. So it depends on the band that you search for. And of course, that will tell you also about the different temperature regime. But also in AGN, you have ultra-fast outflows. So these are the colleagues of the ultra-fast outflows in ULXs, except that this one were discovered much earlier because the set is significantly harder in AGN. And then you have absorption from iron K lines that you can start to resolve even with CCD spectroscopy, and therefore you can find the iron K line. In fact, this was found, for example, back in 2003 from Kenneth Bounds and James Reeves and friends. They start to find that this absorption line, or what looks like a P Cygni profile, that is the authentic natural shape of a wind blowing from the compact object. Interesting early work done by Francesco Tombesi and colleagues show that the kinetic power of the wind would exceed something like 0.51% of the bolometric luminosity, which would suggest that the energy release onto the surrounding medium is sufficient to affect star formation rate. Although this plot should be done not in bolometric luminosity, but in Eddington luminosity. Because if the bolometric luminosity of the AGN is small, because the AGN has a low accretion, then even the energy of the wind is low. So in principle, this should be done in Eddington rather than bolometric thing, which is actually what recently was done by the Subway project using a slightly different sample of object. They found that indeed the outflow rate and energy of this object is pretty high, and X-ray seem to have a more relevant role than ultraviolet photons to push these winds. But please, guys, correct me if I'm saying something wrong, because you are the guys here. Interestingly, the power of the wind kind of seemed to decrease with the Eddington ratio, okay? Due to the fact that perhaps the velocity does increase so much. And I may have something more to tell you about this. There is a good chance that radiation doesn't do all the job, particularly at low Eddington rate. You certainly need other process to explain this extreme velocity. Although I have to be honest, when I see 0.5% speed of light in a wind, I don't know. Calorimeters will tell us whether these are high significance detections. Curiously, ultra-fast outflows are not always found. Sometimes they disappear. Fake detection, or the wind actually disappeared, the duty cycle is low. So that's why what we try is to take an object which vary a lot and perform flux resolved spectroscopy. What we found is that the ionization parameter increase with the luminosity or the Eddington ratio, and perhaps this is why you don't see the wind. If the ionization increases a lot, then there is more sufficient opacity to create absorption lines. So you don't see the wind, but not because it disappears, because it's so ionized that it doesn't produce any more absorption lines. And the velocity also increases, which is what you would expect from radiatively driven winds. But it's not always the case. This object has an even higher accretion rate. It basically is constantly above the Eddington limit of a 10⁷ solar mass black hole. And you can see that when the velocity, the luminosity increases, the velocity goes down. Weird. Why? I mean, you would expect a stronger radiation push. Don't forget that the same thing we also found in the ULX. When there was this additional soft component, there was a cooler, slower component of the wind. So perhaps we are seeing the same. In fact, actually, the increase in the velocity per unit of luminosity, which is kind of similar to 5 minutes, it kind of decrease, the change in the velocity kind of decrease with the accretion rate. So the efficiency of pushing these winds beyond a certain threshold, it's kind of decreasing. So there are many options. One is the following. If you are above Eddington and you keep accreting more and more, the spherization radius will move outwards because it scales with the m dot. And if you launch the wind from outwards, the velocity will be lower and the wind will also be cooler. So you would expect to find an anti-correlation between the velocity and the luminosity. And this could explain what we found in the ULXs and in the AGM. It's one of the possible explanations. Perhaps I'm going to skip this. The only thing I will tell you, I will probably move outwards. There is another thing in common between ULXs and highly accreting AGN, and it's this 1 kV emission line. It's in tidal disruption events, it's in super burst on top of neutron stars, and it's in ULX. Every time you accrete above Eddington, there is a massive emission, and by the way, broad emission lines. And we start to believe that perhaps is either the reflection of the emission on top of the bottom optically thick component of the wind, or is it just the radiation of the wind itself? So it's something necessary to be investigated in the future, because it's really linking these different mass regimes. And perhaps very quickly, we'll only tell you this very interesting result found by Yerong Xu, my former PhD student. He found that when the ultra-fast outflow is very strong, the hard lag, they kind of disappear. So the hard lag is the lag of the light curve in the hard band with respect to the soft one, and it's telling you normally about propagation of fluctuation from the outer disk to the inner disk. So the fact that these fluctuations are kind of disappearing is perhaps telling you that the wind is having an effect on the disk itself, taking away energy and angular momentum, which was supposed to create this hard lag. And we found in 3 sources, and this should definitely be investigated in the future. Outflows look to be energy conserving by comparing different lines, and are also powerful in terms of kinetic energy, although it seems to be less than in ULXs. We are talking of 5%, while in ULXs was 50%, although this was the result with all the data, the gratings and the CCD. So conclusion, winds are found at all mass scales, especially even the fast ones, and they affect the accretion onto the compact object and surrounding interstellar medium. But if you calculate the net accretion rate after you take away the matter with the wind, it seems to exceed the Eddington mean. So super-Eddington accretion can exist. There are some limitations on our understanding of the launching mechanism, the duty cycle of these winds, and the energetics. due to the fact that we have observed with an A3 format telescope for the last 20 years, which was certainly better than the past, but it's not strong enough to do a large sample study or study on short timescales. Which is why in the future, I will probably skip this, Athena will totally resolve and change the way we do X-ray astronomy. But in the current present, the launch of CRISM, which right now, unfortunately, is blind in the soft band, and I can tell you more if you want about this. It provides an interesting extremely high resolution in the iron K band. And in fact, there was amongst several papers out in the last couple of months, there was these two papers on PDS 456, the archetype or prototype of ultrafast outflow AGN, in which it was shown for the first time without any ambiguity whatsoever that the outflow is extremely clumpy in the iron K band, consisting of many clumps. And if you do the calculation properly, now the outflow rate is comparable to the accretion rate rather than being only 5%. So I suspect that calorimetric, even with CRISM, are going to significantly change the way we do astronomy. With Athena would be everything better because of the much larger mirror in particular. And I can tell you, I have some bonus slides if you want to know about the new Athena community, because I'm in the science team, so I can tell you some news also about the coming A&A special issues, which I hope that most of you will join. And these are just some simulation. The only number I want you to focus is this. So with Athena, we will be able to probe kiloseconds timescales, which is what you need to perform flux and state result spectroscopy of these winds and answer important questions regarding the launching mechanism. But we will have to wait for Athena for this. So I will probably skip this. I can tell you more about simulations, but let's leave some time for questions. And I thank you all for letting me.
So questions, curiosities, and the offer the opportunity to ask the bonus. Marcella.
Maybe I can start. Thank you for the talk. I can start with 1313. If you go to the last simulation that you showed for Athena. So you mentioned that in 1313 you have also the FA iron K component, and there is no chance to observe it with CRISM.
There is, but you need something like more than 300 kiloseconds with the gate valve closed. With the gate valve open, you would have a detection in 50 kiloseconds. Not of the iron K. 50 kiloseconds, you will be able to study the lines at 2-3 kiloseconds, but that, sorry, 2-3 kb. That would be fine. The simulation you see here is with the gate valve open. That's why there is a bar on top.
But at low energy.
Yes, but the component that you see here, the hot one, is absorption lines above 1 kb. So that would be also 1, 2, 3 kb. Of course, 7 kb, it's going to be difficult.
Nico.
So, as you showed at the beginning, there is a high degeneracy in the seeding models of high redshift quasars with seed type and accretion mode. Right?
Yes.
So, what would be, in your opinion, the smoking gun for a super-Eddington accretion in a X-ray emitting population of AGN?
At high redshift?
High redshift.
Well, outflows. If you manage to detect outflows with a kinetic power which is larger than the Eddington luminosity, then it would be an unambiguous proof that they're super-Eddington. Because there is,
Because many people, I mean, one of the wisdom and simplification that the community is assuming is that if you have super-Eddington accretion, you tend to observe a steeper spectrum. Is it a oversimplification of the?
No, you're right. In fact, ULX spectra are much softer than X-ray binaries. So if you tend to observe AGN with a slope of 3 or 4, then I would start to believe that the accretion rate is higher. It's a simplification, but I think it's in the right direction. Thank you.
Any other question? I don't know whether there are from home.
Are there any questions from home? People can also speak up. You don't have to. I cannot see waved hands. Nope. So if there are no questions, I can maybe speak 1 minute about Athena.
Yes, I was about to ask.
Okay, thank you. So I'm inside the new Athena science team since last year. So I have to do this, even if I don't want, but of course I won't. I would love to. So the Athena is basically a kind of new mission now, because there is a new profile. We are focusing on specific science goals to convince that that our mission, despite a small scope, is still flagship and can do stuff that right now we can do. So we went through, oh, okay, I have to do it by hand. So there was this massive call a couple of months ago, and I'm really proud of our country, because our country, as you can see in this in this graph, is the one with the largest request. So Italy is the country right now with the largest number of people inside the Athena community. We also had a substantial amount of requests to act as chairs of the panels, and this is the new structure of the panels. Working groups 1 to 7 decreasing by spatial scales, large scale structures, galaxies and supermassive black holes, and so on. And out of this, 4 chairs and co-chairs are Italian. So we proudly have, for example, Maria Chiara Rossetti for the galaxy clusters sample. In group number 3, there is Marco Micheli, Costanzo Giroffi. Then we also for Jacopo Bartolucci in the science of support that focus on theory and simulations. Okay, and the group that is more representative is the Science Working Group 2, of course, AGN and galaxies. I'm not surprised by this, especially because the Italian AGN community is very strong, and Bologna is certainly one of the top institutes to contribute to this. And okay, this was the gender distribution of the people who request to be members. So of course, we really had to fight in order to keep a decent balance for the chairs, and we try to do really our best. In fact, the number of women with respect to men in chairs is overrepresented with respect to the request for example, to join the groups, and we are proud for this. We did really our best. So perhaps the only thing I will close with is the timeline. So you should expect to have by the end of July a call for special issue to join special issues on A&A. It was an idea also for the former Athena mission. So there would be this call, and by I think end of September or so, you should send an abstract about the idea that you have to write a white paper. For example, if you want to write a white paper on performing a study of winds in Seyfert 1 galaxies with Athena, create a team of, I don't know, whatever number of people you believe is sufficient to cover the science, and then you submit your title and abstract. We will then work out on the abstract in the coming month within the new Athena Science Study team, and then by end of October or November, we will let know who's basically going to lead, which team will lead which paper. But in principle, we expect that all community will help with all papers. Okay, we really want an active community for the sake of the mission and the community itself, because if Athena doesn't go through, I have no idea what the X-ray community in Europe will do, perhaps even in the world. So we have to do our best. And there will be also a meeting with all the chairs between November and December. Then from January, there will be massive work, 2026, there will be the massive work on the A&A special issues, and of course, the Red Book. The Red Book is basically a picture of the whole mission that we need to provide before the end of 2026 to ESA, and we expect a lot of contribution from you guys, from the community, in terms of scientific cases and simulations. For example, in this plot, I can show you, I will close with this, that we expect at least something like 20–30% of the red book to be consisting of science case, simulations, and basically why we need this mission. It's just a comparison with other missions. We expect to have something like this. So science is going to be a very important component of this red book. I don't know if you have some questions on this or. I think,
So, given the situation of our friends in US, so this new Athena is likely to be, well, at the moment, is the only real opportunity.
Well, the US are supposed to bail out of Athena as well, so.
Yeah.
Yes, but I mean,
So-
a fraction of 15%. I mean,
Yeah, we'll see, but finger
no,
crossed.
it's not good also for European science.
Yeah, NASA is supposed to build the test detector of the calorimeter. So, it's one of the most important components.
But there is a plan B.
But there is a plan B, but we'll see.
Yeah.
But we are still working on that. So of course, we want to work with NASA as well. It's one of our best collaborators. So we don't want them to bail out.
So we are working to have NASA next year, so but
Yes, please, Nico.
yeah. It's not gonna be easy.
If there's anything we can do, let us know.
Okay, so let's thank Ciro again. What time you leave?
Maybe around 4:30.
Okay, it will be around for a few hours,
Yes.
the third floor, so just in case you have.
I'm in the guest room.
Further
So for
curiosities,
anything
then-
downstairs, guest room. Thank you. And thank you everyone from home. Bye-bye.
Timidi.